So we've got a table, and we're testing to see whether the distribution of applications by card is the same for the past 3 mailing groups. So there should be 2 tests that come to mind when you see a table like this. The chi-square test of independence, which is where you'd see if the row variable is independent of the column variable. And then there's the chi-square test of homogeneity. And so the difference is the confusing part is the calculation is the same. You calculate the expected value the same way as for each row and each column, each cell, I should say. You calculate the same expected value the same way regardless of the test. But the type of test you're doing, it just depends on it depends on your hypothesis statement. So if you're testing to see whether this type of card impacts the mailing, then that would be a test of independence. But surely that's not what's happening, right? Because they're sampling the mailing list first. Like if you get more platinum cards, that doesn't mean there's going to be more in mailing 2 or mailing 3 necessarily. The mailing lists are done independently from the platinum cards. We're testing to see whether the proportions are the same in each group. So whenever you're testing to see whether they have the same proportion, whether the distribution is the same for each of these past 3 mailings, that's a test of homogeneity. Okay, but again, that won't affect the actual calculation. That'll affect the hypothesis statement. So we're not testing to see whether card type and mailing are independent. They're testing to see whether they're the same in the 3 groups or whether they're different. So the null hypothesis is always the no effect model, the status quo. So this, I haven't read through both of them yet, but the null hypothesis should be whichever one is saying that the proportions are the same in each group. The same. The difference is almost always the alternative. If you're testing to see whether the proportions are the same in each group, then the alternative would be that there's some sort of effect happening, there's some sort of change happening, which is H sub A or H sub 1. Okay. What type of test? We know it's chi-squared. We got a table. In this class, if you give it a table of values, it's almost always chi-squared. Chi-squared goodness of fit test, that would be like if you're testing to see whether a pattern of numbers fits like the normal distribution or the uniform distribution. So that's not what we're doing here. We're testing to see whether all 3 of these groups are homogeneous, whether they are coming from the same grouping, whether they have the same proportion. So it's a test of homogeneity, and that just comes from the hypothesis statement. Because in the end, like I said, what we're going to run in StatCrunch to calculate these expected values is a chi-square test of independence, but it's the same calculation. Because I don't think StatCrunch has the word homogeneity as an option. Okay, so we got our table. They would call that summarize. So you go to stat, tables, contingency with summary. And then the columns are these. We're not going to select the total column because each value of the variable is here. And then the row variable, I think, here, let me see if I can move this. Yeah, this is the top cell for the row variable. It's that dash. So I'm going to select that dash for the row variable. That's all this stuff. Expected count, we want that to answer the question. Whoops. What is this? That's not the right one. Expected count, I think that was a different question I was doing. And then, see, they don't have chi-square test for homogeneity, but the calculation's the same. So you hit compute, and there's your expected counts. That's what we needed next. Round to 3 decimal places, it says. So this might be a problem. I think maybe that's 3 decimals. No, that looks like to be 2 decimals. So if StatCrunch only gives you 2 decimals, you can get the actual expected count by taking the row total, just 200 for this top left cell, times the column total, which is 365, and then divide it by the grand total, 600. So 121.667. So StatCrunch almost got it, but we need 3 decimals. You can probably just guess based on the fact that it says 48.33 that it's 48 1/3 there, right? Oh. expected counts, I didn't emphasize this. Those are the parentheses. That's just typical notation. Okay. And then we already have the chi-squared test statistic. I think that's probably on the next note. It's right here. Value is 2.95 to 2 decimal places. And then degrees of freedom, it outputs this right here for us in Excel. 6. Let's see, is that right? No, it isn't right. Okay. That's weird. Why would Excel, why would my stat lab get it wrong? Yeah, because there's 3 rows and 3 columns. So the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So it should be 2 times 2. So that should be 4. So that makes, wait, you got the chi-squared? Oh, no. So it might have something wrong with the p-value then. Let's find out. Yeah, the critical value might be wrong because they're using the wrong degrees of freedom. They didn't even give us a critical value. That's okay. We can get it, though. You can go to stat calculators. It's off screen here. And then there's a chi-square calculator. And then we want degrees of freedom of 4. I think whatever StatCrunch gave us would be wrong. And then we don't want between. We want standard. What's our alpha? 0.05. 1 second. Sorry, I had to refresh myself on what this is doing. You want to delete this, and you want to type in your alpha here. So that'd be the area in the tail. So if alpha is 0.05, you want 0.95. And there's our test, our critical value, I should say. So that's, oops, that's 9.49. We round to 2 decimal places. You get the same answer if you look it up in a table. Degrees of freedom of 4 and an alpha of 0.05. And then what do we conclude? So the test statistic needs to surpass the critical value for it to be significant enough. If it's not, then we can't reject HO in favor of the alternative. So the test statistic is less than the critical value. That's true. We failed to reject HO. Conclude that there's insufficient evidence. Everything looks good. It's not greater than. Failed to reject HO. Clear. Wait, these are the same so far. Okay. This is not independent of mailing. That would be if it was a chi-square test of independence, but we were asked to test whether the proportions are the same. So this is the correct answer. So just watch out for that last part. One's for a chi-square test of independence, and one is for the one we want for the test of homogeneity. Okay, that's it.